Good afternoon, everybody. Please welcome to Center of Excellence SPACE presentation of the codes that are being developed under the COE and its FIL and BHAC. The session is named From Inspiral to Ringdown and Beyond. And today, this webinar can serve as an introduction to state-of-the-art code BHAC designed to simulate accretion flows into compact objects. A short intro of how to use and run your first simulation will be given, and also recent developments concerning the code within the SPACE CoE. And also then we will continue with the FIL code. The webinar will be an introduction to the Einstein toolkit and FIL is designed to simulate binary neutron star collisions using high-order finite difference methods and tabulated EOS. And the tutorial will go through how to compile the ET and run some simple benchmarking simulations using FIL. And our tutors today are Georgios Doulis and Kyle Pierre from the Goethe University in Frankfurt. And thank you very much for coming. Thank you to the presenters for the presentations in advance. And with that, I will pass the speech to the first, and that's Khalil.
Hi, everyone, and welcome to my talk. I'm going to be doing the introduction and talking about the first code, FIL, in this two-part code tutorial. So the title is FIL and BHAC from inspiral to ringdown and beyond. And I'm going to be doing the FIL part, and my colleague Georgios is going to be doing the BHAC part, and we're both under the supervision of Luciano Rizzola at Goethe University. So within our group, we're mainly interested in studying binary neutron star mergers. So a binary neutron star merger is when the remnants of a supernova, the cores of the stars that are left over, come together under gravity, in spiral, and collide, as you can see in this simulation. These collisions are extremely energetic and can be observed. Currently, the gravitational waves can be observed in close by galaxies, but hopefully with the next generation of gravitational wave detectors, these collisions will be able to be observed in the gravitational wave signal right out to the edge of the observable universe. The gamma ray bursts that are produced in these collisions can already be seen to the edge of the observable universe. So these are incredibly powerful events, but they're also incredibly difficult to simulate. So to simulate binary neutron star collisions, we need to do magnetohydrodynamic simulations on a curved background. So we have all the problems of fluid dynamics, of magnetohydrodynamics, of relativistic magnetohydrodynamics, and all of that is on a background that is changing depending on the placement of the matter within our grid. This results in a highly nonlinear set of partial differential equations. These partial differential equations have been shown to be some of the most difficult partial differential equations to solve in not just the whole of physics, but the whole of mathematics. To perform our simulations, the grids that we perform them on have to be thousands of kilometers across, despite the fact that the neutron stars we want to simulate are only 1 or 2 kilometers across. And this is because if we want to extract accurate gravitational wave models, we need the grids to be really huge, even if the neutron stars, the actual interesting stuff is very small. And this is also why we have to use adaptive maths refinement to really refine around the neutron stars in the region of interest, because we need quite high resolution of the neutron stars to accurately model the microphysics we're interested in studying. So we need a resolution less than 100 meters across. Now, obviously, if we're doing that for the whole grid, it just becomes uncomputable with our current computing technology. But there's a lot of microphysics that we can study and that we want to study and we want to include into our simulations. So these include like various different equations of state, different neutrino physics, and a lot more microphysics that we want to include in our models. we have to use high order finite different methods to have accurate simulations. So all of this I'm telling you about because it's just adding and adding to the difficulty and the computational cost of our simulations. We're dealing with relativistic fluids. So we have our fluids are moving very fast. So we need to have very small time steps to accurately model our fluid evolution. There's a lot of variables we have to evolve. For the space-time alone, we have to evolve 30 variables. And for the magnetohydrodynamics, the fluids, we have to evolve 10 variables. So as I said, this all contributes to very expensive simulations to run. In fact, they're so expensive that to model 1 second post-merger, it takes about a year of all time to compute. So after the neutron stars collide, we want to simulate if we want to simulate for even 1 second after this collision in real time, it takes a long time and a lot of computational resources to do. The parameter space that we're interested in exploring is very large, and with how long it takes to do these simulations, it's virtually, well, it is impossible currently to really explore that parameter space in a meaningful way. And we're interested in actually going beyond the 1 second range. The numerical relativity community is very interested in studying the 1 to 10 second range. This is where we hope to find out more about the equation of state of nuclear matter. We want to understand the production of heavy elements. So elements in the periodic table, like gold, for example, are believed to be produced in these neutron star collisions. So if anyone's got any gold on them right now, we believe that this was produced in the collision of these neutron stars, these objects. We want to be able to study how gamma ray bursts are produced, and we want to test general relativity. And to do this, all of this is happening in the 1 to 10 second range, which currently is out of our abilities to study. So we need more computational power, but that means that we need to optimize our codes for exascale computing, as well as trying to use some more sophisticated methods. And I'll come on to that a little bit later in the presentation. The image on the right that you see is the afterglow of the GW170817 event, which was the first observed binary neutron star collision. And from that, we also received a corresponding signal in gamma rays. And this is also one of the goals of the numerical relativity and the astrophysics community in general. It's to study these what are called multi-messenger events, where we get signals both in the gravitational wave signals, but also from gamma rays, also from neutrinos, because each of these different messengers carry different information and help us study different regions of the event to get a more holistic view of the event. So there's a lot that we can learn from these events. So I'm just going to go on to FIL now. So like I said, Georgie will talk about BHAC. And FIL stands for the Frankfurt, Illinois GRMHD code, where GRMHD stands for General Relativistic Magnetohydrodynamics. It's a fully state-of-the-art GRMHD code, and it fully evolves the space-time. It uses box-in-box mesh refinement, fourth order, high-resolution shot capturing finite different methods. It uses tabulated equations of state. So the energies and the densities that are within neutron stars are currently unreachable in the laboratory. So we don't actually understand how matter behaves in these extreme environments. We don't understand the equation of state of matter in these extreme environments. So it's very important that we can have different equation of state models that we can plug into our simulations so that we can test the different equations of state and by observing the gravitational waves, learn how matter behaves in these really extreme environments. So the fact that Phil has this tabulated equation of state scheme is very important for the physics that we want to study. Phil also includes M1 neutrino radiation transport. It's written in C++. It uses MPI and OpenMP, and Phil exploits the Einstein toolkit. The Einstein toolkit is a publicly available evolution framework, and it provides the computational infrastructure that Phil is built on, and that a lot of numerical relativity codes are built on within the community. The Einstein toolkit has been around since the early 2000s and has been incredibly important for the development of this field. Within the Einstein toolkit, we have a module called Carpet, which manages the allocation of memory, the scheduling of functions, the distribution of tasks across nodes and cores, the box-in-box refinement, as well as the grid in general, and the parallel input-output. There's over 413 members from 288 different groups and 50 different countries who are members of the Einstein toolkit, community. You can, in this link here, you can download the Einstein toolkit yourself, and you can play around with it and run some test simulations. And I'm actually going to go through one of the simulations that you can do in a little bit later. And the Einstein toolkit was developed to help us solve the Einstein field equation. To understand the Einstein field equation, to get an intuitive understanding of it, this is a very helpful quote I find from Archibald Wheeler, who was the supervisor of Stephen Hawking, I believe. Space-time tells matter how to move, and matter tells space-time how to curve. So the space-time is encoded on the left-hand side of this equation with this variable g mu nu. The mu nu just stands for the index. In general relativity, we're interested in these objects called tensors. Tensors are multi-dimensional objects, so the indices just tell you what the component of the variable is. So g mu nu is the metric tensor. It contains the information about the distance between points within our space-time, and then r mu nu, which is the Ricci tensor, and r, which is the Ricci scalar, are just partial differential equations of g mu nu. So that's a lot of information. I think the important thing to remember is just that the space-time, how the space-time behaves, is encoded on the left-hand side of the equation. And on the right-hand side of the equation, we have this object T mu nu, which is the stress energy tensor, which describes how the matter behaves. So you can see here, there's this interplay between the space-time and the matter. So the matter moves, and it tells the space-time how to curve, and the curvature of the space-time tells the matter how to move, in a nutshell. So when we want to solve the Einstein's field equation on the computer, we separate the two. So we firstly try and solve the space-time and the stress energy tensor, the matter, separately. To solve the space-time, we use something called the 3+1 decomposition. We take our 4-dimensional space-time, so 4 dimensions are 3 dimensions of space and 1 dimension of time. We take our 4-dimensional space-time and we split into 3-dimensional spatial slices. So on the image on the right, you can see these surfaces. For your imagination, please imagine these as 3D surfaces, and they are surfaces of constant time. So we split our 4-dimensional space-time into these hypersurfaces, we call them, and the surfaces are described completely by the spatial metric. Now, these slices are embedded in a 4-dimensional space-time, and that is described by this object Kij, which is the intrinsic curvature. when we perform the 3+1 decomposition of our Einstein's field equation, it results in a set of evolution and constraint equations. And depending on how you do it, your evolution equations can be hyperbolic partial differential equations, which are very nice for numerical simulations because they're numerically stable. The first development of this 3+1 split resulted in equations that were elliptic, I believe, which aren't numerically stable, which blow up which blow up and cause your simulations to result in nonsense, basically. So when we do the 3+1 split, we we use these variables to describe the connection between these different hypersurfaces. We use alpha, the lapse function, which measures the proper time between adjacent spatial slices. Beta I, the shift vector, which measures the change of coordinates from one spatial slice to the next. N is the unit normal to the hypersurface, so it just points in the direction of increasing time. So if the spatial surfaces are constant time, N points perpendicular to these spatial surfaces and just points in the direction of increasing time. And T is a vector that represents the direction of evolution of the coordinate time. So when we apply our 3+1 split, our metric tensor, which I described before, looks like this, equation 2. So this is the generic form of the metric tensor if it is split using the 3+1 decomposition. And then it results in these evolution equations, like I said. Now, this is the ADM formulation. So this is the formulation which is not numerically stable and it's elliptical. There are other formulations like the BSSN and the CCZ4 formulations, which are hyperbolic and are numerically stable, but they're huge. And so I couldn't include them on this slide. So just to help you visualize the equations, this is the evolution equation. There's a lot of detail here, but I think you should focus on the partial differential of the spatial metric in equation 3. So it's just evolving the spatial metric, which describes the hypersurfaces. And then equation 4, it's a partial differential of the extrinsic curvature. So it's describing how the 4D space moves. Another thing to maybe pay a little bit of attention to is at the very end of equation 4, this S minus E and this Sij, which are the decomposed form of the stress energy tensor. So this is how the matter re-enters into the evolution equations. So if I was dealing with a black hole, for instance, where I don't have any matter, I could set these terms to 0 and they would come out of my equations. But if I want to include matter, I need to calculate what these terms are, the S minus E and the Sij. And to calculate that, we have to calculate the evolution of the fluid. So we're separating the space-time evolution and the fluid evolution, and the fluid is an input into the space-time evolution. I hope that all makes sense. If not, please, in the Q&A, you can ask me to describe this a little bit more or a little bit more clearly. As well as the evolution equations, we get a set of constraint equations. These constraint equations are solved initially at the start to give us frame 0 of our simulation or the initial data of our simulation. So say I want to simulate 2 neutron stars colliding. Well, I need to create a grid with 2 neutron stars in that grid with momentum, angular momentum, energy, etc., etc. And to do that, I have to solve these constraint equations with the specific assumptions that need to be made to describe a neutron star. Now, these constraint equations are solved at the first time step or before the first time step to get our initial data. But mathematically, they should be they should hold, if they're solved at initial time, they should hold for all time. Now, because we're doing numerical simulations, they're not respected for all times. And the constraint equations are violated because of numerical errors in our simulation. So we can use these constraint equations to get our initial data, but we can also use them to track the numerical error. So it can be kind of a good trace of the numerical error within our simulation and where the numerical error is distributed in our simulations. So that's how we evolve the space-time. Now I'm going to talk about how we evolve the fluid dynamics. So for each spatial slice, as you saw, the stress energy tensor comes into the evolution equation. So for each time step, and in fact, for each sub-time step, if we're using for the Runge-Kutta methods, which we normally do for numerical accuracy, the stress energy tensor must be calculated for every one of these sub-time steps. The stress energy tensor for an ideal MHD fluid is dependent on what we call primitive variables, which are the rest mass density of the fluid, the pressure of the fluid, the free velocity field of the fluid, and the magnetic field strength. And the evolution of these variables is governed by the constraint equations and the homogeneous Maxwell's equations. So for equation 6, the first one on the left-hand side is the conservation of rest mass density. That just says within any fluid element, our density is conserved. The amount of matter is conserved. The middle equation describes the conservation of energy and momentum, and the equation on the right-hand side is the homogeneous Maxwell's equation, where F asterisk mu is the joule of the Faraday tensor. So the Faraday tensor is what describes magnetic and electric fields. And we use this formulation, the joule of this, which has a very precise mathematical definition that you can look up, and it helps to simplify our equation. Now, for relativistic fluid dynamic simulations, to evolve them, we use something called the Valencia formulation, where we take the equations in 6 and that we rewrite them until they're in this form. All of them, where they're in this form where we have a flux term, which is the Fi, and a source term. The conservative form, the conservative variables are given here in equation 8. And it's the conservative variables, not the primitive variables, that are evolved at each time step. And we do it like this to conserve mass, energy, and momentum to truncation error. This is standard practice within all relativistic MHD codes. So we start with the primitive variables, which describe our stress energy tensor. We convert them to the conservative variables. We evolve the conservative variables, but then we need the primitive variables back. And to get the primitive variables back, we need to use a Newton-Rhapsody root finder algorithm, which in numerical relativity codes is always one of the most expensive algorithms. And we need to do this so that we recover the primitive variables so that we can calculate the new evolved stress energy tensor, so we can put that into the space-time evolution equation so that we can then evolve forward in time our space-time variables as well. And so that's kind of the generic, that's the theoretical background, and now I want to do a small hands-on tutorial. Just going to stop sharing for a second and then reshare. So, like I said before, FIL uses the Einstein toolkit. FIL is a module of the Einstein toolkit. Or in the language of the Einstein toolkit, modules are called fawns. So if I change between modules and fawns during this description, which I might do, just know that I mean the same thing. Modules are fawns, fawns are modules. FIL is a module of the Einstein toolkit. So FIL is a private code currently. We're hoping to make it open source by the end of the SPACE project, but currently it's a private fawn. But FIL is a more sophisticated, more state-of-the-art fawn of fawns that already exist in the base Einstein toolkit. So I'm going to show you how to run a TOV star in the base Einstein toolkit. And it's exactly the same as how you would run a TOV star using FIL, but you just have to put in the FIL modules, the FIL fawns into the Einstein toolkit, and then it will create a TOV star with more accurate simulations. So to run the Einstein toolkit on your device, you need to install some software packages. So this tutorial can be found on the Einstein Toolkit website. And this is just a list of the packages that you need to install if you want to run the Einstein Toolkit, depending on your different machine. I use Ubuntu, so these are the different packages that I had to install to run the Einstein Toolkit. This is just a little bit about setting up the notebook. So it just allows you to use bash commands within the notebook, which is useful for what we're trying to do. Okay, so once you get the tutorial up, you can go to this, when you do it yourself, you can go to this part of it, downloads, where you can download the Einstein toolkit. So we can just download it from the Git repository. Now, like I said, the Einstein toolkit was developed in 2002. So at the time, you didn't have this GitHub. I don't think GitHub was a thing at the time. So they definitely didn't have the organization function that GitHub has. So to get the fawns, to get the modules of the Einstein toolkit, we need to go to each GitHub individually and download it for the different modules of the Einstein toolkit. But the people in the Einstein toolkit have kindly created some scripts that make that very easy for you. So you can get all these modules just offline, online. And these are the base modules of the Einstein toolkit. These are the open source ones. And then people in the numerical relativity community often have their own private fawns that just plug into the Einstein toolkit and can be run. Okay, that's finished running. So as you can see, there's a lot of different fawns in the Einstein toolkit. And once we download them, we then cd into our Einstein toolkit directory. This is the wrong directory. It should be cd codes / Okay, nice. Okay, so Cactus is where the Einstein toolkit lives. Cactus is the name of the framework that the Einstein toolkit uses to fit in the different modules. Hence the name, sorry, Cactus is the framework, and then the fawns, the modules, plug into this framework. This is why it's called, these are why in the Einstein toolkit they refer to them as fawns. I'm going to share my command module just so you can see what the Einstein toolkit looks like. Okay, so this is the directory I downloaded the Einstein toolkit into. We can go into Cactus. So here's where the Einstein toolkit lives. And inside the directory arrangements is where all the active forms live. So these are all the modules that you want to use for your simulations. Some of them always have to be used, like the Cactus base. What else? Cactus numerical, which contains the Runge-Kutta methods. And some of them you can turn on and off depending on the simulation that you want to run. By the way, if you want to interrupt at any point with a question during this tutorial, please feel free to do so. So what else can I show you? So inside the par directory is just basic parameter files that come with the base version of the Einstein toolkit. So we're going to be running this .par file in our tutorial. SimFactory has been developed recently, and it's supposed to make the experience for new users as easy as possible. So SimFactory contains submission scripts, run scripts, configuration scripts. So you can use the SimFactory commands to run your simulations, and then it will manage everything for you. And then the fawn list contains the fawns that are going to be actively compiled when you compile the Einstein toolkit. Okay, let me just go back to the Jupyter notebook. Oh. Okay, let's just do it like this. Yep. Okay, so if you want to use the SimFactory, the first command you put in is this .simfactory bin sim silent setup. And this just creates a file with some of your information. Let's have a look at what the file looks like. So you guys can see the command module, right? So this is the file when you run that command that's created, and it contains some of the information of the machine that you're running on, some like information like your email address and stuff like this can be put in so that you can get notifications when your simulations are done. And also some information about like the number of processors that you have, the number of threads that you can use. But the most important things to pay attention to are these. So the generic.cfg, the CFG file, the configuration file contains the flags that you run your simulation, you compile the Einstein toolkit with. And it contains the locations of the modules that you want to run. The generic.sub is a submission script for submitting your jobs, and the generic.run is a run script for running the jobs. Tutorial. So when you want to compile the Einstein toolkit, you can use SimFactory again to make the experience easier. I would run this now, but the Einstein toolkit takes a long time to compile. With 2 cores, it'll probably take about 15 minutes or so to compile. So I compiled a version earlier on Leonardo, so we can just go there and we can just have a look at that. So once you compile the Einstein toolkit, inside this directory, inside this execution directory, you'll find your executables. And if you saw here, we named our executable sim. So then our executable will be called cactus_sim. So you can change the name and you can have multiple different executables. Now, it works like this because your fawn list, you can specify different fawns to compile. So this means that if you want to do different simulations, you can compile different amounts of fawns if you want to shorten or lengthen your compile time, or if you're running completely different things, or if you're testing things. All this is to just say that you can have multiple executables in this folder, and that you can keep track of them nicely. Okay, so the first thing that we can run is this just this hello world statement. Just copy that. No. Sorry. I did this a little bit earlier, but then I deleted everything so that I could run it smoothly the first time. But I forgot to do that. Okay. And then this should run. So when we run this, just forgot to do the environmental variables again. And that means I have to go back and delete that simulations. Okay. So let's run this now. Okay, there we go. So when we do this command, we just get a bunch of hello world statements. Not so interesting, but when we do our CI/CD, that's the first thing we do because we can just check to make sure everything's working from a first glance. Okay, so we want to run something more interesting. So we want to run a TOV star, which is our stationary, static, non-rotating star. So we want to simulate how a star behaves. To run on the Einstein toolkit, you need to have a parameter file. As I showed you before, the TOV parameter file comes prepackaged with the Einstein toolkit. So you can run this on your own machines. At the beginning of any parameter file, it will say the active fawn, so the active modules that need to be included to run your simulation. It will give you some conditions to terminate, to end your simulation. Some conditions to terminate if something goes wrong. And then the grid parameters is where you set up your grid. So here you can see X min, Y min, Z min, X max, etc. You can set the grid spacing of your grids. You can say when your AMR regrids. So here it regrids every time step. You can define the number of centers. For a static TOV star, we only need one, so we just put one. And then the number of refinement levels is set to 2. So we just have 2 refinement levels, and the radius of the refinement level is set here. We can also define our boundary conditions. We're going to use reflection symmetry because our TOV is a symmetric. So this means that we're gonna simulate one 2D quadrant of our TOV star, and because it's symmetric, then we can just assume that will be the same for the other 3 quadrants. Okay, let me just go through this and see if there's anything else I want to mention. The number of ghost zones can be specified. The time step, the order of the method. So here we've got an RK4, but you can also replace this with all lowercase Euler, and that'll do just the Euler method. But you won't get very accurate results for your binary neutron star simulations. For TOV, I think it might be okay. A NAND checker, and then here you can define your hydrodynamic variables, your curvature variables. So here we're using the BSSN formulation. So I mentioned in the presentation, there was the ADM formulation, which was not numerically stable. The BSSN is, the CCZ4 is, Z4C is also another formulation of the 3+1 decomposition that is stable. Okay, it's more technical stuff. This is where your initial data is specified. You can specify the central density of your TOV star, the equation of state that you use. So we're just using a polytropic equation of state. You can specify your input-output, what variables you want to output, basically, and the file type that you want to output. So that's what your parameter file is generically looks like. It's got something at the start about the termination, about the grid, about the time integration, about the hydrodynamic variables, the space-time variables, the outputs. So that's what the parameter file looks like. Let's run a TOV simulation. Let's see. So this command just creates a directory in my simulations folder. So all the data for my simulations will be held in this simulation folder, and for the TOV, it will be this TOV.et folder. The command specifies what executable I'm going to use. It says what configuration file I use. So where to find the modules that are used in the compilation, and where to find the flags that are used as well. I think this is more for posterity, so that you can check you can recreate your simulations. A submit script is generated, a run script is generated, and then in my command here, I say where the path file is, and then in this simulations directory, the path file is saved. So the sim factory, like I say, is used to kind of abstract as much as possible to make the user experience as easy as possible to run a simulation. Okay, we can then run a simulation. Okay, everything looks good. Everything looks good. So that's how we submit it. This is the command to submit our simulation. We're running it on 2 cores, 1 thread, and 20 minutes of wall time. We can check what simulations are being run. So there's one active job, which is the TOV job that I've just submitted. So that's good. And then we can follow along with the output with this command. Okay, So here we're just seeing the maximum density of our TOV star as our simulation runs. Now you can see that the maximum density is oscillating a little bit. This is perfectly normal. We expect for an analytical solution for the central density to remain the same, but because we're doing numerical simulations, there'll be slight perturbations, and this will cause oscillation of our central mass density. When we run any job, yeah, we can just track the progress of the job here. And if we want to cancel a job mid-progress, we can then use Control-C, which will exit out of this window, but will also close down the simulation. Okay. This part of the tutorial, Jupyter Notebook just tells you about where the simulation directory is and just how to run some commands to keep track and to keep clean your simulation directory. But let's go to the next part and let's plot our results. So Qubit is a visualization software that has been developed by the creators of the Einstein toolkit to help us visualize the outputs of the Einstein toolkit. So I've copied the data from one of my previous runs of the same TOV file onto my home machine. So I should be able to just run it. Yep. Okay. Okay, I'm just gonna get rid of that line. Doesn't matter anyway. Okay, just loading some modules. So this includes Qubit, which is used to visualize the data. And from Qubit, we can get this simdir function. So we take it to the data directory where our data is stored. We apply this simdir function, and what it will do is it will just look through the directory recursively, and it will find any data files within any directory that you specify with the outputs of a Einstein toolkit simulation. So you have to be a little bit careful where you specify the data directory, so you're not recursively looking through hundreds of directories for your data. Okay. Once we've run our data, once we run this, we can plot our data. So here we see the pressure, these dotted lines. This is what our simulation outputted, and the cold pressure is what we expect the simulation to output. So everything looks good here. And then we can also visualize our output. So let's visualize it here. And here we can see our TOV star. So we've successfully done our TOV star. We can specify what iteration. So this is just the first frame. We can just change that number, and we can view the other frames of our simulation. And yeah, this is pretty much it. Is there any questions? Okay, I see I've got some questions in the chat. So what is the list of equations of state that you use in your solutions? I don't have an exact list on me, but the equations of state are generated by different theoretical frameworks. So in our group, we've got some people who specialize in nuclear physics, and they create different equations of state depending on what physics we want to include. And then we can create a table and of like the pressure, the pressure, the density, the temperature, and then Phil can actually interpolate between points on the table to find points that aren't included within that table to then include in the in your model of your binary neutron star. So for your second question, yes, you can use your own equation of state. If you generate one of these tables and you can put it into Phil, you'll be able to generate your you'll be able to use your own equation of state. And yeah, we do have an interest in using exotic equations of state. Like I said, the equation of state for nuclear matter is unknown, so we use different equations of state.
So Khalil, I don't know if the others have seen this, but I put an answer in the chat saying that any equation of state that is cast in a suitable form, which is the one set by the composed database, and there is a link. I don't know, can you see my answer to the question?
Yep, I can see the answer now.
Yeah, okay.
So, okay, nice. I haven't seen this before, actually. This is very cool. Okay, so yeah, we can see the different equations of state.
Yeah, maybe you should go to the home page and
So you use Lorraine to obtain models of rotating magnetized neutron stars, see the EOS composed class. Okay, so I think it's saying that you can use Lorraine to generate equations of state. Is that right, Luciano?
No. I think some of these equations of state are also using Lorraine, but Lorraine is to compute initial data.
Okay.
So, but the short answer is, yes, if you have your equation of state, which you like so much, all you have to do is put it into a suitable form, which means, have a proper list of quantities in the right order, pressure, density, energy density, whatever. And this is all specified in this database. And once you have that, you can just attach it to the simulation, ask to read a specific file, and you'll be done.
Okay, then. If there are no more questions, then oh wait. Marisa, do you want to ask, or is this to hand over to the next person? No. Okay. Okay. Let me just do the introduction for Georgios then. So like I said, we want to do long-term simulations, so that's 1 to 10 seconds post-merger. And within the Goethe University group, we've been developing a new way of doing this. Also, my colleagues have been developing a new way of doing these long-term simulations using a hybrid model that combines both FIL and BHAC. So unlike FIL, BHAC is not a fully GRMHD code. It doesn't fully evolve the space-time, is what I'm trying to say. It uses a conformal flatness condition, a conformal flatness approximation to partially evolve the space-time. And this reduces the number of equations that need to be evolved to evolve the space-time from 30 to 8. And for 3D models, BHAC has been shown to be 6 times faster than FIL. However, this conformal flatness condition has to be used for very axisymmetric spacetimes. So it cannot simulate in spirals, it cannot handle rapidly changing spacetimes, cannot model gravitational waves. But we can use it to model the remnant object. So after the 2 neutron stars have come together and combined, then we can model the remnant object using BHAC. On the right-hand side, you can see a comparison for a head-on collision where the red line is the FIL where it's fully evolved, and then BHAC using its conformal flatness condition evolves the remnant object after a head-on collision. And you can see they agree pretty well. And then here, I should have just a 2D simulation of a post-merger remnant object that is evolved in BHAC and FIL. And now for more details on BHAC, I can hand you over to Georgie.
Good. So thank you for joining the second part of this training series. So I'm going to talk about BHAC. Thanks to Khalil, who made a really nice introduction of GRMHD and numerical relativity, so I don't have to say almost anything about that. And I can proceed in describing some basic stuff about BHAC, and then I'll show you how you can download, compile, and run your first simulation and plot your first plots with BHAC in just 15 minutes. And I'll say some very few things about BHAC porting to GPU. So BHAC has been developed in Frankfurt by a number of people. You can see them here, some of them. So the first release of BHAC was in 2016. And it has been designed as a state-of-the-art code to simulate accretion flows into compact objects in stationary spacetimes. So here are some examples of what can we, simulate with BHAC. So here we have some, pictures of the behavior of matter around a spinning black hole, around a Kerr black hole. So here we see the mass density, and here we see the magnetic strength. And here is how it's viewed from the z equals 0 plane, and here from the y equals 0. Here we see some more detailed, pictures of this here. So we can see the black hole and how the behavior of matter is evolving with time from left to right. So some facts about BHAC. So it's a multidimensional code. So we can use it in 1, 2, and 3 dimensions. So as I said before, solves the GRMHD equation in stationary background. It's second order accurate and uses finite volume and high resolution shot capturing methods. So during the introduction of BHAC, Khalil mentioned BHAC+, which is currently developed by several people in Frankfurt. It's extension of BHAC and can include space-time evolution and other features like neutrino transport. And but on this talk, I'm going to talk about BHAC. So BHAC is part of the space project and not BHAC+. So BHAC has adaptive mesh refinement, which is based on a usual octree block-based approach. So this AMR is provided by the MPI AMR VAC library, which is publicly available, can be found in this link here. So BHAC is built on top of the AMR VAC. So this is why they're both written in Fortran, and they both use MPI for parallelization. So BHAC is publicly available in this repo here. So we're going to clone this repo in a few minutes and show you how can you install BHAC on your computer or in any cluster. So the next slide is about the AMR structure in BHAC. So here we have a we assume you have a 2D grid. So on our computational domain, when we have something in a vacuum or something that doesn't need a lot of resolution, then we have this, the basic, the L1 level of our AMR, and when things are starting to get more complicated, then we can resolve better our grid. So we see here that we have these smaller boxes. This is on the L2 level of the AMR, and here is on the L3. So when we have, oops. So when during parallelization, we have somehow BHAC has somehow to choose how to annotate, the blocks that our computational domain is, separated to the resources we have. So for this, BHAC is using the so-called Morton-Norton curve. So let's assume that we have here our computational, two-dimensional computational domain is composed of 27 blocks. So, and let's say that we are running on four MPI processes. So what BHAC is doing is that divides 27 with 4, and we have, so on each MPI process, it will allocate 6 blocks, but in the first 3, because we have 3 blocks left, it can be divided exactly. So it will give 1 additional block to the first processes. So here we can see that it starts from down left and gives these 7 gray processes to the first blocks to the first processor. Then it gives the next 7 gray blocks to the second processor, and then the next 7 white in this order to the third processor, and the last 6 to our fourth one. Yes. So let's see some basic functions of BHAC. So BHAC is a hydrodynamics code. So it has, it's using finite volumes methods to solve the germ MHD equation conservation form, employs several Runge-Kutta schemes for the temporal evolution, supports a number of different coordinate systems, a number of different equations of state. There are a lot of reconstruction schemes implemented, Riemann solvers, and this is the interesting thing. So it has implemented 3 conservative to primitive conservation routines. So they work as backup strategies of each other. So when the one fails, then we're using the next one, especially in regions where the magnetic fields are very strong. It has implemented a couple of divergent control methods, and the AMR that I just explained, where the fixed refinement ratio between 2 successive levels is set to 2. And it's also multidimensional. So here, that's one of the main applications of BHAC that most of you know. So BHAC has been used to produce the synthetic images of, for example, of the black hole that it's residing in the center of our galaxy. So it's used by the Event Horizon Telescope collaboration, and it has been employed to produce the first images of a black hole. So the data produced by BHAC are used as an input for the BOSS rest tracing code in order to produce the accretion flow and the black hole images. So currently, BOSS is being replaced by BH-LITS, which is a GPU-based ray tracing code. So this shows, that porting also back to GPU, it's really important because it has to be in line with the new ray tracing code that it's going to use, the output from BHAC. And by porting back to GPU, we'll have higher accuracy and more time, longer in time pictures like the one you can see, videos like the ones you can see on the right. Now, before I start, I show you how to, install BHAC on your computer. I'll just show you some scaling tests that have been done. So here we have done scaling tests on BHAC, on HAWK, a machine in Stuttgart, and also on two Euro HPC machines, Leonardo and Lumi. So BHAC scales quite good, up to several thousands of cores, which it's quite good indication that it can be run in parallel. So I'm going now to show you how can you install BHAC on your laptop or on any cluster. So can you see my terminal?
Yes.
Good, thanks. So the first thing we do is that, okay, we create BHAC tier. So inside here, we're going to clone, BHAC. So BHAC will be cloned from the website I showed you before, one that's publicly available. So we just copy the URL and we come back, take some seconds. Yes, so we're done. So BHAC is very close. So this file contains all the code for plotting, for simulations, everything. So we'll create another directory, which we call backgrounds or simulations as you want, where we are going to have all our simulations, the par files, the SLARM files, the output, everything is going to be there. So before doing that, we have, of course, to load some modules. So to compile and run BHAC, it's enough to have a recent version of the GNU compiler suite and recent version of OpenMPI. So it would be better that this OpenMPI it's compiled using the same GCC version. So another point is that we have to define, where is our code living. So this would be really useful in the following. So we define the BHAC tier. So you see it's just your home directory. And here is the, what we cloned, the code we cloned from the repo. And also this is important for the visualization afterwards, which tells Python where to find the visualization tools. So by doing that, I'm sourcing it. Good. And now we enter the backgrounds. And now, I show you at the beginning, some nice pictures of, accretion into a Kerr black hole. So we are going to run that simulation as an example. So we have to copy all the power files and all the material that we need to do that. So this is into the code. I'll show you. I have written that also later, so you can find all this in the slides of the presentation. So here, and what we want is this one. So we just copy paste it in the background directory. Yes. Enter that. So here we see that we have a par file, a make file. So a big difference with other codes that BHAC has is that one has to create one executable for each application. So, you know, here we don't have, BHAC doesn't have inbuilt only one application, you know, it has a, one can see here it has a spherical accretion, it has a shock tube, it has a commissar torus. So it has a lot of applications. So the big difference of BHAC with the other codes is that we need an executable for each application. So for example, FIL that Khalil talked before, you know, it has one executable which can be used for all the applications. So here now, we see we have a make file specific for this application. We have a par file. So what we're going to do now is to create the executable for the fishbone torus. So to do that, we have first to specify, nope. We have first to specify, you know, the setup. So this is given here. So we just copy paste that inside here. I'll explain it while during the compilation, I'll explain to you what all this means. So we set up and then just make clean and make. So compilation will take 2 minutes. So during that time, let's go through what we need to do to compile BHAC. So we have to load the recent version of the GCC and OpenMPI, create a BHAC directory, and then inside there, clone, you know, BHAC from the public directory that I have provided to you. We have to define the path to this code that we just cloned. And then we have to create a BHAC runs or BHAC simulation directory, get inside there, copy paste the application we want there. And then we'll make the output dir in a while because there all the output and the information about our runs are stored. And then we have this. So this is the setup. So the first one, it's the dimension. So we have a 2-dimensional setup here. Here, this has to do with the ordering of our variables. And here it says that it's a GRMHD simulation. Here is the equation of state. We're using modified Kerr-Schild coordinates. And this is the architecture. So, you know, if someone is using Intel, you know, there are a lot of different architectures already existing in BHAC. So here we're using the G-Fortran, and this 10 means that our version of G-Fortran is later than 10. If you have a earlier version, then you just erase 10. Also, if you have Intel, there are also similar, you know, architectures that will help you, you know, to compile BHAC. So this one here, it's an interesting. So this is specifying, you know, you remember that, you know, BHAC is dividing the computational domain in blocks. So here we're specifying how many cells are inside each block. Of course, this is including also the ghost points. In the specific simulation, we have 4 ghost points on each side. So actually, we have 8 ghost points. So this means that each one of these blocks will have on the R direction 16 cells, and on the X directions, theta direction, 8 cells. This can be, you know, changed. And so in this way, comparing this with the number of cells we want to use in our simulation, we can change the number of blocks that our numerical domain is divided. You know, we can even have one block that is covering the whole computational domain. Okay, I think that now compilation, we're finished. It took a couple of minutes. So this is here our executable. Here are, you know, the libraries that were built during the compilation. So now we have to make the make_dir output directory where all our, you know, output and information about our simulation will be, you know, put. Now let's take a look at the par file. So I'll just go through. Okay, sorry. So here that says us where to put the output data. You know, this is why we have to create the output file. So it has to be the same name convention with the file we have created. So here we have to choose, you know, how many iterations before the simulation is stopped. Here I'll just I won't use the maximum number of iterations, but the maximum time, which I'll set to, for example, 10. Then here, yeah, here, this shows you the ghost points. So this shows you the ghost points, and this is the number of cells in the R direction and theta direction. So, you know, we use 192 points on the R directions, and when we set up, you know, back, you know, here, you know, we used 16. So this means that we have 12 blocks along the R direction, and the same thing for the theta direction. So we'll have 12 blocks along the R and 12 along the theta, which means that we have 12 and 12, so 144 blocks. So in this simulation, our computational domain will be covered by 144 blocks. Okay. Let me see if yes, I set it to a small number. Good. And now we need a SLARM script. Okay. I'm running that on Carolina. So the supercomputer of our partners from IT4I. And sorry. So here. So that's a usual SLARM script to run on Carolina. So yeah, this, you know, everything is, you know, quite familiar, but, you know, in order to run BHAC, so we need this execution command. So one can see it here. Yeah, so this is the execution command we need. And this is exactly the one I'm writing here. And so we are going to use 8 MPI processes, and each one of the processes will be, you know, will use 16 CPUs. So that's a full node, CPU node of Carolina, which has 128 CPUs. Okay, so let's run that. Okay, so it's all good. It will take around 30 seconds to compile, so it already started compiling. So next, I'll just show you how can we plot our results. You know, if we look in the output folder, we see that there are already, you know, some files produced there. So for example, I'm going to show you how you can simulate the initial, you know, conditions, which are in this file here. One can track the simulation using this log file. So, you know, the first is the iteration, the second one is the time. So we see that we have reached already the final time. So our simulation is actually finished. Yeah, it's completed. So what I'm going to show you how one can use the tools already in BHAC in order to simulate, the initial phase of this of the application that we're using. So so we use the IPython version. So yep. Now, if you remember, the path that we specified at the beginning is because now IPython knows where to find these two Python files that are, contain the scripts for reading, loading the data, and also plotting them. So we have to import them. Good. And then, this is the way that we're loading, this file here for plotting. So here is the 0. If we want to specify which slice we want, you see that up to t equal 10, every delta t, dt 1, we have one, file output. So we specify which one we want using this 0 here. If we want, the second slide, we use that as 1. Here we want the initial condition, so it was already loaded. And then here we specify the grid. It will take some seconds. Yes. And now we can make our first plot of a simulation with BHAC. Will take some seconds. Okay, takes a little longer. Yep. So this is here a plot of the initial configuration. So here we have the Kerr black hole, and this is the distribution, the initial distribution of matter around it. So that's a visualization of the output result we had before on Carolina. So okay, let's return to the presentation. So I have here, let's go through again of how can we run. How can we run BHAC? So we use this executable here, and we just have to be, careful that BHAC doesn't allow the number of processes to be more than the number of blocks. So let's say that here we used 8 MPI processes. So if our computational domain it was chosen in such a way that, for example, it had 6 blocks, then BHAC would complain. So the number of blocks must be at least equal to the number of MPI processes that we're working. So that's something that one has to be careful. Otherwise, it's quite straightforward. So for the plotting routine, I said that we have to specify this Python path and then use these commands to plot our first picture with BHAC. So I think that, in 15 minutes, we manage, to clone, compile, install, run, and plot our first picture with BHAC. So it's a very user-friendly, very lightweighted program that it's really quite friendly also to any kind of machines, laptops or clusters. Okay, now I'll conclude with back on GPUs. So first, we decided that BAC will be ported on GPU initially on a unigrid for the following reasons. So the AMR BAC framework that BAC is built on, it's not GPU portable, although they're in process of porting it. The time frame, it doesn't fit in the SPACE time frame, and also it's actually not necessary for our goals, to GPU port AMR BAC, and that's because for two reasons. So the increase in the time when we use for the same simulation unigrid instead of AMR, it's about 36% increase in time, which can be very easily compensated if we have a GPU acceleration of 30 or 40 or more. And the other reason is that actually the data used by Bosch, to create the synthetic images of the black holes are unigrid. So, staying unigrid and porting back to GPU on unigrid, it's totally fine for our purposes. So what have we done? So following the experience of other partners in the space project, we created a mini BAC, a mini app of BAC, which is just a smaller, more compact version of BAC, which has all the basic utilities of BAC. So according to them, it's easier to proceed to the GPU porting of a code when you have such a mini app. It's like, having a Christmas tree without the decorations. So this is what it's the BAC mini app. It's doing what I showed you before, but without additional, features that can, mask the actual computations done by the code, and can just increase the execution time, which we're not interested in that. So, several modules have been GPU ported already. So, for example, the conservative primitive methods, the Riemann solvers. And a couple of months ago, we had the first fully ported single GPU version of BAC. So we have run validation of the current version of BAC and on CPU to CPU and GPU to GPU. So we compare the current version of BAC with the original one, and we see that our results, the results of our simulation agree. So some preliminary tests are showing a 4-fold speed up, but that most probably is half because of some issues we have with the scaling of BAC on Carolina, where these tests have been done. So for the future, we have to further optimize the ported modules so we can increase this speed up that we already see. And also we have to move to a multi-GPU implementation of BAC. Okay, this is all I had to say about BAC. Thank you very much.
Thank you, Georgios. Maybe a comment. I would say the stripped down version is like a Christmas tree without the decorations, but with the presents at the bottom. I mean, it's still doing something interesting.
Yes, that's true.
Okay, so
Yeah.
if there are no more questions, I think we can finish it. And I thank you for your talk, and thank both of our tutors today. I would like to ask our participants if they could complete our satisfaction survey. I put the link to the chat, so please, it will be very helpful for us. And I hope to see you soon on our next webinar, which is 1st October. So thank you, and wish you a nice rest of the day.